All right. Welcome, everyone. It's 4 o'clock, so I think we'll get started. So today we're very happy to have Scott Lawrence returning to us to give us our physics colloquium. So Scott did his PhD at the University of Maryland with Paolo Badacchi before coming here for a postdoc. So he was here for 3 years working with Paul Ramachki. Left in 2023 and went to Los Alamos, where he's currently in the theory division as a Feynman postdoctoral fellow. So Scott is a theorist with an appetite for very challenging problems. He's worked on sign problems in Monte Carlo, out of equilibrium dynamics, all kinds of interesting things. And I think today he'll give you a little sampling of that with his colloquium. So Scott, please.
All right. Thank you, Ethan. And thanks to all of you for being here. Today I'll be talking about sort of challenges in computational physics with an eye towards quantum systems and the quantum systems we care about most. I'm nominally a nuclear theorist, so the quantum systems we care about most in nuclear theory and high energy theory and some condensed matter. This picture is, so this is a picture taken a little bit west of Los Alamos. There's a national preserve called Valles Caldera. As you can tell, it's called Caldera, so there was a dormant volcano there. And this valley you're seeing is a large valley, creatively named Valle Grande. And you can see something a little striking in this picture, which is that the floor of the valley is flat, and there are no trees on the floor of the valley. There are 0 trees on the floor of the valley. And you rise a very short distance onto this hill, or onto the hills on any side of the valley, and all of a sudden you're just surrounded by evergreens. It's a very sudden transition. And the reason for this, I was trying to look up what's the reason this happens. As far as I can tell, one of the main reasons this happens is that at night, cold air cools and falls into the valley. And so the floor of the valley is actually substantially colder than even if you go up 100 feet. And so young trees simply can't survive that, and so there are no trees growing in the floor of the valley. And maybe it also has something to do with the differences in the soil, and so on and so forth. But what I'm struck by, when I see things like this, what I'm struck by is just this thought that if I wasn't shown this picture, if I was just shown the topography of the region and asked to predict what trees were there and where they were, I do not think with 10 years of studying I would ever get it right. And that's sort of the feeling, that's sort of the feeling that motivates this talk is, what could we actually figure out about physics without being able to see experiments? Nominally, there's a whole lot that that the standard model is supposed to predict. But if we were actually trying to make those predictions and we did not have the benefit of measuring many, many quantities in a lab, how much of it would we actually get right? So that is the spirit of this talk. Please feel free to interrupt and ask questions. I believe there's a microphone to be passed around. So, OK, we're all more or less familiar with the standard model. At least we've heard a great deal about it. Right, so you have the fermions, of which the up and down quark make up most baryons that we're familiar with, in conjunction with gluons, which are providing the mass of these baryons, like the neutrons and protons. And these standard model fields, there's sort of this story where, OK, at very, very short distances, you can talk about quarks and gluons and electrons. At somewhat longer distances, the quarks and gluons bind into neutrons and protons and other mesons and other hadrons. And then you start talking about nucleons. After the nucleons themselves bind into nuclei. So you have sort of a nucleus at the core of an atom and a bunch of electrons wandering around it. And then from there, we're now in the domain of chemistry or eventually biology in describing or material science, in describing how these atoms make up physical matter that we're familiar with. Fundamentally, at the bottom, it is all supposed to be a consequence of the standard model. And we believe we know to a pretty high precision what defines the standard model. It's the standard model Lagrangian, which defines the dynamics of all of these fields. And so the particles you see are what you see in a collider, but the consequences of the standard model include ordinary physical matter and whatever else you want to ask a question about. Now, the part of the standard model that is famous for making verifiable predictions is quantum electrodynamics. So we're just talking now about the charged fermions, mainly like an electron and a positron, and the photon. And quantum electrodynamics has the remarkable property that there's a sense in which it is close to a free theory. So by a free theory, I mean a theory in which you take two particles, you try to set up a scattering experiment, you send them by each other, and they just keep going in a straight line. They don't see each other. In a free theory, we can compute all consequences analytically. There's very little to compute. And QED is close to a free theory. And this fact helps us compute, to very high precision, the consequences of quantum electrodynamics, this theory of electrons and positrons and photons. The marketing copy for QED says, in big letters, this theory gives you the most precise predictions in science. And this is more or less true, as far as I can tell. So the spectrum of hydrogen is something one can compute with some help from a computer, but initially done with pen and paper, to around 1 part in a million, maybe a little better. The anomalous magnetic moments, so the magnetic moment of the electron, for example, is a famous, very high precision test of QED, and that's been verified to around 1 part in 10 to the 10. These are all very round numbers. Please don't murder me when your paper has a slightly better figure and I didn't include it. Others, the verification is less good. Like electron-positron scattering, as far as I can tell, we're only verifying electron-positron scattering cross-sections to around 1 part in 1,000. But this is a check that is limited by experiment. It's not that we can't compute in QED what the electron-positron cross-section would be. It's just that it's very difficult to measure that precisely, whereas the anomalous magnetic moments are very popular because we can make very precise measurements of them. So when you look at these numbers, you should think work for experimentalists, for the most part. But not entirely. And there's sort of an exception that proves the rule here, which has been in the news for a few years, which is the anomalous magnetic moment of the muon. Right? So the muon is the sort of fundamental fermion, much like an electron, but substantially heavier. Right? There it is, third row, second column. And the anomalous magnetic moment of the muon has a contribution which comes from quantum chromodynamics, another part of the standard model, which doesn't have the property that there's this small coupling constant that we can expand in. And so that measurement, right, and so this is sort of the Feynman diagram that is showing the anomalous magnetic moment of the muon, and there's that big ugly blob labeled QCD. The theoretical prediction of this magnetic moment is hampered by QCD, among a few other things. It's a little more complicated than that. But one of the big difficulties is getting a high-quality QCD prediction has proven difficult. And it's not that QCD needs to give a prediction to 1 part in 10 to the 10, because the QCD prediction is already suppressed by powers of this QED coupling constant. And so the precision needed from QCD is much smaller, and QCD is unable or has great difficulty doing that, although now it's sort of able to be competitive with experiment after a great effort. So one way about thinking, back to QED for a moment, one way about thinking about these very high precision tests of quantum electrodynamics, like ordinarily you would say, OK, quantum electrodynamics predicts lots of things. It predicts magnetic moment. It predicts scattering cross-sections, and so on and so forth. And you just have this bevy of predictions, and it's kind of a mess. So what you can do instead is you can say, QED makes one prediction. And the prediction is, if you measure the coupling constant alpha, which is the fine structure constant, in 2 different ways, you will get the same answer. That is the prediction of QED. And then QED specifies a bunch of ways in which you can measure alpha. And so people do this game. And so you can go through the literature over more or less a century of physics, and you can look at the best possible, the best measurement of alpha that's been made. And right now, measurements of alpha are, as sort of we saw from the magnetic moment, around 1 part in 10 to the 10. But there's been this very steady progress. And now we find out if any of you can see the laser pointer. Can you? Oh, wow. OK, I can't. So there's been this very steady progress over the course of a century, very straight line on a log linear plot, until a few years ago. And so I invite your predictions as to what will happen in 10 years, whether this ankle will persist or whether it'll go down again. There have been other bumps before 2000, and the slope was shallower before 1960 as well. So, but this is the history of the precision of measuring the fine structure constant. And it sort of is a showcase of the power of quantum electrodynamics and our ability to do perturbative calculations. But not all of the standard model is perturbative. And the part of it that describes most of the mass in everyday life, which is quantum chromodynamics, chromo because there are supposed to be 3 colors of quarks. Let's say that the theory predicts they're red, green, and blue, if you enjoy thinking that way. Here, there's a coupling constant, again, much like the fine structure constant. But the problem is that this S, it's called alpha sub S, and the problem is that this S in the coupling constant stands for strong. This is a strongly coupled theory. And so perturbation theory is just not very good for a lot of questions you want to ask, a lot of natural questions. It turns out, due to asymptotic freedom, perturbation theory is excellent at sufficiently high energies. But most of the questions I want to ask about QCD are not at sufficiently high energies. Sufficiently high energies means high enough energies that neutrons break apart. And my day-to-day experience does not involve, thankfully, very many neutrons breaking apart. So perturbation theory suffers from this problem, among others, that you can't see hadrons in it. You can't see the fact that there should be bound states. There's another computational approach, which has sort of grown to be, I would say, dominant in QCD, certainly over the last decade, called lattice QCD. And lattice QCD, I will not describe in detail how it works. This is not a lattice QCD talk. But it works very well at moderate energies, moderate or low energies, and low densities. So you have a few protons or a few neutrons in a box. And it works well in equilibrium. So one does not easily ask questions about scattering in lattice QCD, because that's not an equilibrium process. Instead, you ask questions about what is the mass of a proton, or what happens if I heat some region of space up to some hundreds of MeV, of mega electron volts. And this is, I don't know if this is a knowable reference. This is a reference to a poem I once saw. But as you can see, there are quarks inside of a nucleon. The original poem said, apple, 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 forever. It was in the shape of an apple. And then there was one word, worm. I suppose that's not a particularly famous poem, but this greatly amused me when I made the figure yesterday. So this is the problem with QCD. So OK, let's look at the predictions that QCD makes. Now remember, QED, best predictions are of the order 1 part in 10 to the 10. There are lots of predictions that are 1 part in a million or better. QCD, I tried to take a somewhat fair sample of questions one could care about, but they're biased. These are questions that I personally tend to care about. The proton mass, very good, very precise prediction from lattice QCD, 0.3%. Okay. The hadronic contribution to this muon magnetic moment, so this is a contribution to what would otherwise be a QED calculation, around 1%. It was very important to get that to high precision. And the lattice community is still working on it, but more or less has. Event shapes, so in a high energy collision, sort of where the energy is going. This is done in perturbative QCD. And these very ballpark figures are around 2% accurate and verified in experiment. And a personal favorite of mine, because my old boss, Paul Romachka, worked on this a lot, the shear viscosity of the quark-gluon plasma. So if you take 2 heavy ions, like gold, and collide them at high energies, there's a very brief moment where the state of matter called the quark-gluon plasma is created. And it's sort of high temperature and moderately high density QCD. Not particularly high density QCD. And in fact, I believe this calculation is done at 0 fermion density. And so this is done, for instance, at Brookhaven National Lab at the Relativistic Heavy Ion Collider. It's also observed at the LHC. And this thing acts like a fluid. It's a bunch of particles in a small space, and they're strongly interacting. So the thing acts like a fluid. And if you put momentum into one part, the momentum will also affect other parts of the fluid. The ability of the momentum to diffuse through the fluid is called the shear viscosity. We would like to know from QCD what it is. There's some QCD prediction. And very ballpark numbers, we know this from theory to around 25%. And it is in rough agreement with an experiment, where there are also pretty large error bars on this value. People will debate this number, of course. Other things I might care about, I'll take two relatively light nuclei. I don't care what they are. So let's say 2 carbon nuclei. This is something that could happen in a star undergoing fusion, for instance. I'll scatter them, and I'll scatter them at energies large enough that the carbon nuclei can break up. So it's inelastic scattering. There's no QCD prediction that's been computed from this. There is a QCD prediction. We don't know what it is. The mass and half-life of, without loss of generality, everyone's favorite nucleus, fermium-257. Raise your hand if that's your favorite nucleus. There we go. OK. So the half-life from experiment, if I remember correctly, this one is in some number of hours. It is a long half-life relative to the microscopic scale, not because there's some very small coupling constant, but just because there's a quantum tunneling process that has to occur. And again, QCD prediction unknown. Doesn't mean we don't know what the mass is, just means we don't know that that mass is in fact what QCD would predict. We can't test QCD by looking at samples of fermium-257, which are lying all over the place. Lastly, fragmentation functions. This one is a little bit more obscure. But if you have a very high energy collision, then there are these high energy QCD disturbances that you think of as quarks and gluons. Ordinarily, at high energy, you think QCD consists of quarks and gluons. Well, as these disturbances propagate outward, away from the high energy center of the collision, they must eventually be confined into hadrons, into protons, or neutrons, or pions, or whatever, some asymptotic massive state of QCD. The manner in which they do this and the distribution of hadrons you get is called a fragmentation function. Sort of the story is that the quark is fragmenting into all these heavier particles. And again, QCD prediction, not available. There's a prediction. We don't know what it is. And to finish beating the dead horse, the poor precision that you're seeing here, it's a property of the calculations we're performing, not the theory. QCD makes very precise predictions for all of these quantities. I simply don't know what they are. I can't put them on the board in front of you. OK. Now, sometimes when you are getting a prediction from QCD, you're not going to do the whole calculation in QCD. This would be a little insane. So I'll give you an example of what I mean. I go and I do a lattice QCD calculation, or better yet, I have Tom do a lattice QCD calculation for me. And he comes back and says, do you feel honored? He comes back and says, QCD does in fact predict that there are neutrons and there are protons, and here's how they interact. Here is the potential between them. This is a thing that you can, in principle, extract from lattice QCD. And then I say, great, that's a prediction of lattice QCD. Now, that prediction defines some theory. It's some effective theory of nucleons. I can take that effective theory and run with it and do a quantum mechanics calculation and determine the binding energy of, say, the deuteron. Right? The deuteron is a bound state of a proton and a neutron. And if you know the force, if you know the effective potential between these two particles, you can work out the binding energy. This is a thing you can plausibly do in your undergraduate quantum mechanics class. That final prediction for the binding energy, it wasn't done in QCD, but it is a prediction of QCD. Because I started with QCD, I made one deduction, and then I made another deduction. So this trick of sort of using an effective theory to amplify your computational power is a common one way or another, and it's a totally valid one. So for example, if you're writing things in terms of mesons and baryons, you're often working in something called chiral effective theory. Here, all hadrons are degrees of freedom, which are fully dynamical. Another effective theory often used is the one I just described, where you just say, look, there's neutrons, there's protons. They have forces between them. And for instance, one of the sets of forces between them is referred to as the argon potential. It was written down in the 90s and early 2000s, and it's very effective in predicting binding energies of light nuclei. Right. So here is, these are sort of examples of the calculations we can do that, in principle at least, could be considered predictions of QCD. I should note that the argon potential is fit to data. It's not actually a prediction of QCD, but it could be, so it will round for the purposes of this talk. So you can study nuclear structure, and there's an algorithm for studying nuclear structure. The story sort of goes, I have some particles which are evolving under the Schrodinger equation, and I look at the Schrodinger equation, which is here, and I say, this looks quite a lot like the diffusion equation. I mean, you have to get rid of an I, and there's like a biasing term due to the potential, but other than that, it is the diffusion equation, and I know I can simulate diffusion on a classical computer. So how can I use this in an algorithm? It turns out that if you think of yourself as evolving not in time, but in the imaginary component of time, okay, if time was imaginary here, this I would cancel. This would be a diffusion equation, right? So if you think of yourself as evolving in the imaginary component of time, this is equivalent to projecting onto the ground state. So you can study ground states of the Schrodinger equation by simulating the diffusion equation. And this is more or less what people do in order to study the ground states of light nuclei. And it works up to a point. And sort of you can get up to 10 or 20 nucleons fairly reliably. There's a pretty good review paper here, if anyone wants to look at it, by Carlson et al. Yeah, please interrupt.
Without the I mean, it's just going to blow up. This equation blows up with V. Or you certainly don't conserve the norm. And then
The norm is not conserved. I don't think it blows up. It becomes larger. There's no like singularity in time, is what I mean to say.
Well, if there's some regions of positive V,
They'll increase.
Huh?
Of negative V if I get all the signs right. But yes, the regions with negative V will get larger and larger weights over time. That's correct.
So
but there's also a drift term. And so those regions will contribute larger weights to the regions near them. And this is in fact reminiscent. This is in fact like what happens in the ground state physically, right? You prefer in the ground state to have more weight in the regions of larger negative V. And I suppose it is not obvious from looking at the diffusion equation, but there is in fact an equilibrium. And that here is something you'll just have to take on faith, I guess. I don't know how to prove that right now. But now the equilibrium, to be clear, the norm of the state you have will not have an equilibrium. So the norm will just be increasing or decreasing over time. And like that's a moderately irritating computational problem. But it turns out nothing more than that, because of course you can add a constant to the potential without changing anything. You care about the state. Its norm is meaningless. And so what you tend to do in the algorithm is add a constant to the potential to minimize the extent to which the norm is changing, just because it's computationally inconvenient, not because it's physically necessary. OK. All right. But this is not a calculation of scattering or any other sort of real-time dynamics. And even using these effective field theory tricks, like scattering is still an inaccessible thing in practice, at least inelastic scattering, right? Scattering of two bound states that break up, like two carbons. OK, well, what can we do about that? And I'm sure everyone here is familiar with at least the hyperround quantum computers, which will save us all. In fact, there's a natural use of quantum computers. And there's this lovely quote by the mathematician Norbert Wiener, which is, the best model of a cat is another cat. I don't think he was thinking of quantum computers. But the best model of a quantum system is another quantum system. And the point of a quantum computer is that it is a well-controlled quantum system. It's a quantum system where if we want these 2 degrees of freedom to interact in thus in such a way, that can be arranged. This allows us to sort of take this quantum system and fine-tune it into being a model of the quantum systems I actually want to simulate, like a few nucleons bouncing off of each other in a box, far from equilibrium. I will not talk in great detail about the hardware behind quantum systems. There are some major competitors, including companies that are in this region. But you sort of have qubits that exist on very cold, superconducting material. It's very cold, so they don't interact much with the environment. This is necessary in order to keep the quantum system well controlled. You don't want sudden interactions with the rest of the world that change the state of your system in ways you don't understand. because that's not what's happening in your nuclear system. Similarly, you have like trapped ions, right? And it is important to keep them segregated from everything else. So this is the idea behind quantum computers. We're going to have a quantum system which is well controlled. And you can think of this, I like to think of this as entirely analogous to how most classical simulations work. Not all, but like almost all. When you think about a classical simulation of a physical system, probably what you're imagining is this sort of scheme. Let's say you want to simulate the wave equation, OK? So there's a set of states that the system can be in, right? The system, I'm going to simulate the wave equation. I have like a string, and there's some wave on the string. And so the string at every point in the x direction has some y coordinate. It might be very close to its equilibrium value, or it might be quite displaced. There's some displacement. And there's a set of states. But my classical computer also has a notion of a set of states. The classical computer has a bunch of bits on it. And each string of bits is one state the classical computer can be in. If I have 10 bits, I have 1,024 states. If I have 20 bits, I have 1,000,000 states, and so on and so forth. So what we do is we say, look, I'm going to assign to each physical state a string of bits, which will represent that physical state. And if I put my computer in a physical state, that is, in the string of bits that represents that physical state, I know it'll stay there because there aren't too many cosmic rays hitting it or whatever. And then there are some rules. The equation of motion up here, the wave equation, gives us rules for how to go from one physical state, one position of the string, to another. And I say, that's great. I'll implement those rules on my bits. And then I'll just apply them over and over and over again. And I'll see how my string moves through time by seeing how the bits move through time. Right? I evolve for some period of time. I look at the bits. I plot what the wave is supposed to be. This is how you can go ahead and simulate the wave equation or many more complicated PDEs. Motions of rocks, wildfires, whatever. So we're going to do the same thing on the quantum computer. And this whole scheme of you should be able to use a quantum computer to efficiently model a quantum system is usually attributed to Feynman, who wrote about this and I think gave a talk on it some decades ago. But it's a natural thing, because I say, well, I have a well-controlled quantum system, and that should be computationally useful. So on the classical computer, a state was a string of bits. On a quantum computer, the state is now a superposition of strings of bits. And to be clear, there was a set of possible strings of bits. I take every element in that set, and I say that's now a basis vector in some basis space. And now a state is a vector in this basis, in this vector space. Sorry, every string of bits is now a basis vector in a vector space, and now a state is a vector in this vector space, not necessarily a basis vector. So here's a sort of typical state that I can have on my QPU, which is a CPU, but Q. And the state of the physical quantum system, the thing I want to simulate, very, very similarly. It's also some superposition. And I can also list a complete basis, in principle, of states that the quantum system could be in. So you follow the same procedure. First, you list all the physical states. And you pick a nice basis for the physical system. This might be like position basis. You say, here are all the positions this particle can be in. Very good. Then you pick a mapping. You say, how am I going to, given a list of bits, how am I going to assign a basis state? And then you take the operators you're interested in, which will include the Hamiltonian, and it will include whatever you want to measure. And you figure out how those operators act on the qubits, and in particular, how you can, on your quantum computer, accomplish the same operations on your qubits. And then finally, the sort of hard step that I won't talk much about here, but just to warn you, it turns out that very frequently the most difficult part of any quantum simulation is preparing an interesting initial state. There are lots of initial states you can easily prepare, but they tend to be sort of high energy and nonsense, nothing like what you would see in ordinary matter. And so there's some difficulty in getting to an interesting initial state. Not that it's impossible, but that's the part that ends up requiring the most thought very often. So a quantum simulation follows these steps. To give you a more concrete taste of things, let's think about a quantum field theory. So a quantum field theory, for the purposes of this talk, you can model it as follows. At every point in space, there is some quantum degree of freedom. If you like a harmonic oscillator, then let it be a harmonic oscillator. If you like quantum spins, let it be a quantum spin. It doesn't matter. The illustration here, clearly, they're quantum spins. So at every point in space, you have a quantum spin, and these are coupled to each other. And maybe there's some overall magnetic field. And so you can write down a Hamiltonian, much like this one, where at every point in space, you have a magnetic field. And for every neighboring 2 points in space, never mind what that phrase means, for every neighboring 2 points in space, there's a coupling. The spins would like to be aligned in the z basis. And the standard model is a quantum field theory. The predictions of the standard model should come from simulating a theory much like this one. And we can simulate this on a quantum computer. First, you say, OK, well, I'll just represent all of these spins. Each of these is, in some basis, either a 0 or a 1. So clearly, a state of my physical lattice is also a state of a bunch of qubits, which are all 0s or 1s. And to evolve the Hamiltonian, we use something called the Trotter-Suzuki decomposition. You can also sort of think about this as a Floquet dynamics type thing. Essentially, if you have a Hamiltonian which is rapidly varying, then the system will act like it is being evolved under the time-averaged Hamiltonian. And so this is how the Trotter-Suzuki approximation works. And this allows you to simulate quantum field theories as long as you can sort of describe them in this language as a lattice of quantum degrees of freedom which evolve under a known Hamiltonian. The QCD, quantum chromodynamics, is a gauge theory. If you want to read about how to simulate a gauge theory on a quantum computer, I very biasedly recommend that paper. How many qubits are needed for this sort of task? So I picked a few representative tasks and very sketchily estimated how many qubits are needed to get a lot of useful, interesting information from these simulations. QCD fares the worst, by far, where millions or tens of millions of qubits to start getting useful information out of QCD. The properties of materials are substantially, depending on how you do it, substantially lower qubit costs. 10 to the 5 may be pessimistic. Nuclear structure is a little lower still, since you don't need a very large box. If you just want to find out the mass of a heavy nucleus or where all the particles are, which for very heavy nuclei can't be done very well classically today, you really only need maybe 1,000 or a little less than that. And for scaling things, the limit of classical simulations is around 50 qubits. So if you have a plan to run something on a quantum computer and you require 30 qubits, that can be done today with a sufficiently large supercomputer. OK. I want to, yeah, go on.
That's kind of a big number, 10 to the 7. 2 to the 7.
So these things are relative. And there are numbers bigger than that. No, this is not an optimistic number. This is a number you look at and go, OK, well, that's not what I'm going to compute on a quantum computer in my lifetime. Yeah. Or to some extent, you say, OK, well, maybe this number is very pessimistic, and maybe I have clever tricks. And so there's some effort to come up with clever tricks to more efficiently simulate. But for stuff like QCD, I don't know of plausible simulations that are lower than 10 to the 5, I think. I mean, yeah, it's a big number. This is why QCD is not the first thing we will simulate on a quantum computer.
Is that assuming error correction or no?
Yes, sorry. Not even talking about error correction in this talk. All qubits are assumed to be perfect qubits. They are already error corrected. Feel free to multiply by another 10 to the 5 or whatever. Depending on the fidelity of your physical qubits, you may need sort of very large numbers of physical qubits. And I also have not discussed the amount of time the calculation would take on the quantum computer. I usually view the bigger obstacle for the simulations I'm interested in as just the raw qubit cost. There are some calculations where even a very short amount of evolution would be quite interesting. And so as long as you can do things in parallel, it's the qubit cost that really worries me. Certainly for QCD, you look at the qubit cost and you immediately know you're in trouble.
How many nucleons are in the universe?
How many nucleons are in the universe? More than 10 to the 7.
More than 10 to the 7?
Yes.
No, but you're, like, what's the point? I mean, it's not.
10 to the 50 is my rough ball. That might be embarrassingly off. Feel free to correct me.
This is now 2 to the 10 to the 7 Hilbert space of the size of 2 to the, let's say it's a qubit.
Ah.
So that's what I'm confused about. But that's
No, the Hilbert space, when I say 10 to the 7, that means the Hilbert space is of size 2 to the 10 to the 7. There are 10 to the 7 qubits,
right, 10 to the 7 qubits
which means the dimension of the Hilbert space,
is 2 to the 10 to the 7.
yes.
So that,
And that's more than the number of anythings in the universe, which is why we're never going to write down that Hilbert space with a classical computer. Okay. Sorry, I feel like I didn't answer the question.
I'm still
Processing? OK, next slide. OK, so let's talk about like a different physical problem. Also of great interest to me. I started out as an undergrad in astronomy, actually, and so I was studying rapidly rotating neutron stars. And so for whatever emotional reason, I care a great deal about the mass-radius relation of a neutron star. So a neutron star, you can sort of tell from the name, it has a lot of neutrons in it. Ballpark numbers, like 90% of the baryons inside, you would expect to be neutrons, maybe 10% protons, very ballpark. And we are able to observe now with the neutron star interior composition explorer, called NICER, the light you see from a rapidly rotating neutron star. So imagine you have this very compact object. Its mass is around a little higher than that of the sun, but its radius is just like 12 kilometers or something. And there's a bright spot on it, and it's rotating. And the bright spot comes into view and comes out of view, and you see a flash. And it comes into view and comes out of view, and you see a flash. And so you get, over time, you get this sort of waveform. And this waveform isn't perfectly symmetric because of effects of redshifting and effects of general relativity. So from the exact shape of this waveform, you can attempt to figure out the mass of the neutron star and its radius. And you can try to make these measurements by fitting against the predictions from general relativity. And so this is a somewhat large industry. Nuclear physicists produced a whole, this is the radius, this is the mass. Nuclear physicists have produced a whole bunch of plausible predictions for what the mass-radius relation could look like. What we know now, it appears that the maximum, the heaviest neutron stars that we found are around 2.1 solar masses, somewhere around here. So all of these equations of state that don't manage to accomplish 2.1 solar masses must be wrong. And the typical radius of a neutron star, something like 11 kilometers, 12 kilometers, with error bars that everyone will fight about, but let's say plus or minus 1.5 kilometers. And given the equation of state of nuclear matter, you can predict in general relativity the shape of a neutron star, its radius and its mass. And it's called the Tolman-Oppenheimer-Volkoff relation. You take in the pressure as a function of density. It spits out. It's an ODE. You just evolve it. It spits out the radius as a function of mass. So the shape of a neutron star, the mass-radius relation, is a prediction of QCD. You just need the equation of state of dense quantum chromodynamic matter. And out comes a curve, one of these curves. And every neutron star you observe should be on that curve, up to, if it's rotating quickly, it gets distorted, and so on and so forth. OK. So lattice QCD does not help us with this problem. It turns out there's something called the fermion sign problem, which more or less renders the non-perturbative techniques we have available to us inapplicable. And the energies involved are low enough that perturbative techniques are not really applicable either to studying neutron stars. So we're left a little bit in the wilderness. And I want to more or less end this talk by discussing sort of a new method which at least doesn't care very much that there is this fermion sign problem. It's not affected by the fact that there's a high density of fermions. So let's go back to sort of the basics of quantum mechanics. There's a Hilbert space, and there's an inner product. And if you have a vector v in your Hilbert space, a state, and you take the inner product of v with v, you get a real number which has to be non-negative. This is just one of the axioms of quantum mechanics. And this has more or less far-reaching implications. So you can think of a quantum mechanical state as being characterized by a wave function. You're likely used to writing down wave functions, but you can also just characterize it in terms of expectation values. You can say, on average, here's the position x where my particle will be. And here's the standard deviation of its momentum. If you measure its standard deviation, if you measure the momentum, then you'll be somewhere in this distribution. And you could predict how x and p are correlated. These are all expectation values of operators. And the consequence of positivity is that if you have any operator O, think of it as a matrix, the expectation value of O dagger O, the inner product of O with itself, has to be non-negative. Sometimes this is obvious and not useful. The expectation value of x squared can't be negative. That isn't very surprising. It's a standard it's a variance of a probability distribution. We're not surprised. But sometimes this is a less trivial statement. And you see this in quantum mechanics for the first time when discussing the uncertainty relations or the ground state of the harmonic oscillator and its ladder operators. X plus IP, daggered, is x minus IP. And so this product has to have expectation non-negative. And as a result of this, x squared plus p squared has to be greater than or equal to 1. You would not immediately have thought this. After all, we just said x squared has to be non-negative, p squared has to be non-negative. So we know that x squared plus p squared has to be non-negative. But there's a stronger statement. It, in fact, has to be larger than, imagine there's an h bar there. It has to be larger than h bar. All h bars are 1. This is the uncertainty principle written in a slightly different form. It's the reason why the ground state of the harmonic oscillator has energy which isn't 0. And it turns out it's much more powerful. And it can be used to prove many things about quantum systems. So yeah, this is the harmonic oscillator example, which you're used to. And one way of writing it is sort of rewriting the Hamiltonian in terms of a dagger A plus a constant. And a dagger A, you know, has to be non-negative because it has the form a dagger A. So clearly, this constant is the lower bound on the ground state energy of this Hamiltonian. This is called a sum of squares proof, very creatively, right? Because we rewrote the Hamiltonian as a sum of squares. In this case, there's only one square, but that's still a sum. The general rule is that you take a basis of operators, and you define a bunch of linear combinations of those operators, these capital A's, and you rewrite the Hamiltonian as a sum of a daggers A plus an overall constant. And that gives you a lower bound on the energies of that Hamiltonian. You can never, the Hamiltonian can never have an eigenvalue which is lower than C. There's a fact I won't prove here, but it's enormously computationally useful. The space of sum of squares proofs is a convex space. Now, if you've thought about numerical optimization, you know that convex spaces are very nice. The point of a convex space is that we can efficiently optimize some function over it. So to be clear about what I mean by a convex space, the blue space is convex. If you take 2 points, then the line between those 2 points stays inside the space. Red space is not. We have 2 points. We draw a straight line between them, and it goes outside of the space. And the problem with non-convex spaces is if you try to do some minimization, you know, the naive minimization algorithm, right, is you drop a ball right here, and you let it roll downhill. The problem is it's already downhill. It's not going to go anywhere. If you jarred it a little bit, it might drop down into this local minimum, but you're not going to find the true minimum. Non-convex spaces are very difficult to optimize over. Convex spaces are comparatively extremely easy. So we can use this. This is now a computational method, because we say, look, I have this family of proofs of lower bounds on my Hamiltonian. It's any sum of squares decomposition. And the space of sum of squares decompositions is convex. So I'll just optimize this constant C. I'll maximize it. And that will, once the algorithm terminates, be my bound on the ground state energy. And it turns out this is a practical algorithm for lots of systems. One of the early systems that was studied with this was back in 2011 by, and let me get the names right, Barthel and Hübner, I believe. And this is the TV model. It's a sort of simplification of the Hubbard model. You have just fermions, one species of fermion, no spin, hopping around a lattice. It's related to the Hubbard model, which is in turn closely related to models of unconventional superconductivity, high temperature superconductivity, things we want in the search to understand in the search for room temperature superconductors. So this was studied via sum of squares proofs back in 2011, and sort of results caricatured here. There are more modern techniques in the realm of sum of squares proofs. It turns out you elaborate on this method some, and you can get, among other things, not just a lower bound on the ground state energy, but also an upper bound on the ground state energy, which you could have already gotten via variational methods, and also bounds on just about any operator in the ground state, lower and upper bounds. So you can really get full information about the ground state by doing this. At least in sort of small quantum mechanical systems, including like small lattices of fermions. And remember, a lattice is the baby version of a quantum field theory. So, and sum of squares proofs have been used far beyond these simple quantum mechanical systems. So just to highlight a few of the results that have come out in the last 5 years. So originally, this stuff was sort of brought to the attention of the high energy physics community by the conformal bootstrap, which constructs very large sum of squares proofs to study the behavior of conformal field theories. That is, field theories that are scale invariant. As you zoom in or zoom out, their structure does not change. There's a good review dating from 2018. The key results in this were derived in the 2010s. And then after that, miscellaneous quantum mechanical systems that you might study in your undergrad quantum mechanics class were shown to be solvable via this method in 2021 by Berenstein and Halsey. Lattice field theories, of my interest, obviously. You may have gotten the sense in this talk is in studying lattice field theories. And so generalizing this method to various tasks you would want in a lattice field theory has been most of what I've worked on. Towards quantum gravity, there's a matrix model called the BFSS model. I will not remember the names, and I don't want to embarrass myself by guessing. But this has been studied as well with some success now. It's still being pursued with sum of squares proofs. There's no other plausible computational method for it. And you can also not just study the expectation values in the ground state. You can use this sort of method to study the real-time dynamics of a quantum system, which is not really accessible. You can study Hilbert space sizes that are not really accessible to any other method this way. OK. To conclude, sort of I have this mental map. I don't know that this is a good map of the space of quantum computational problems, but it is the one I have, and I thought I should share it. I sort of think that there as being two things that make a quantum problem very difficult to study. One is having a large fermion density, which, to be clear, is fermion-antifermion asymmetry. If you want to think about this in other terms, particle-hole asymmetry. Cranking that up induces a fermion sign problem. Sort of an extreme case here is the mass radius curve of a neutron star. The neutron matter equation of state is sort of maximally hard as far as fermion density goes. When the fermion density is low, though, you can talk about like baryon masses or the deuteron binding energy. And these are pretty easy problems. We can also ask about the distance from equilibrium. Is this a ground state or a thermal equilibrium state, or is this some dynamical system? And being farther from equilibrium tends to make things harder to study, even theoretically. So baryon masses, obviously, those are in equilibrium. A proton just sits there. But we cross the boundary of classical computation pretty soon. QCD hydrodynamics is pretty far. There's some moderately far from equilibrium stuff there that is interesting. Nuclear fission. You have both problems. You have both the fact that you're far from equilibrium, you have a system breaking up, and the fact that you're at quite high fermion density. It's already difficult to just get the binding energies. And with that, are there any questions? Thank you.
Great, thank you. We do have time for some questions.
For the microphone.
Thank you. Could you go back to slide 13 really quickly? So I think earlier on you mentioned that like some predictions about neutron stars were QCD wasn't able to predict so far, right? How did they get those curves?
So if these curves were predictions of QCD, there wouldn't be 20 of them, first of all. These curves are given by nuclear model builders. So most of them, trying not to say anything too blunt. One thing you could imagine doing is sort of saying, I'm going to first write down a nucleon-nucleon force and compute what happens at moderate to low densities and try to extrapolate. You can say, I have a guess of the behavior of the symmetry energy, so the energy penalty for having more neutrons than photons, and so on and so forth. These curves are not predicted in general from a Hamiltonian. There's some sort of fit to some low energy data with some extrapolation, maybe fitting to expected high energy behavior as well. But that is all. Yeah. I have never myself produced one of these curves, so I cannot give you the details of how any of them are produced.
Other questions?
Can we look at the slide that shows the accuracies of various QCD calculations?
Yes.
There it is, yeah. So I know as an experimenter, sometimes we're lazy and we measure and measure and measure until someone tells us we get the right answer. And I'm sure that theorists are not subject to that same sort of laziness.
Of course not. Theorists are perfect.
Yeah, but
And there definitely wasn't just a 5 sigma announcement of the mu on G-2 that was gone.
Okay. Where I'm going with this is I look at the right-hand column,
Yeah.
and those look suspiciously similar. I'm just wondering to what extent they're limited by the experimental number.
Okay.
As that gets bigger and bigger, as the experimental number gets bigger and
Yeah.
bigger, it makes me a little suspicious. Not that I would ever suspect
Smaller and
anything.
smaller, I hope you mean.
I mean, say I look at the shear viscosity of the
Yeah.
Clark wood, and the accuracy of that's 25%, which sounds a lot like the accuracy of the experimental number.
It is the yeah.
Yeah.
So
And then
first
the-
of all, I
and then
should
the-
first of all I should clarify that number in particular I ballparked.
Okay.
Because the calculations of it can be controversial.
Yeah. Yeah.
And so I just sort of said this is around my sense,
But
and I hope nobody kills me.
I just wonder, like the one that's the best number, 0.3%,
Yeah.
happens to be the one that the experimental number is really, really good on, and so you can
I
keep
think the experimental number is far better than 0.3%.
Yeah, that's what I'm saying. Is that but is it can you do as well as 0.3% because you've got a good number to shoot at? Is what I'm asking.
So on that one in particular, I don't want to draw sweeping conclusions. But on that one in particular, I think there's just a coincidence, which is that masses happen to be experimentally pleasant, and light, few body masses in lattice QCD happen to be computationally pleasant. I should point out that there's also going to be a very high precision calculation of the mass of iron 56. Wow. Sorry, I misspoke. A high precision measurement of the mass of iron 56. That's a thing you could measure in a lab without much trouble, to quite high precision. That's not something we can compute in QCD to high precision. So there's not a perfect alignment between what there's high precision on here. And in particular, I don't think, although I am a skeptic and a grouch, I don't think that this is evidence of that sort of phenomenon. Okay. Despite, I agree that there's some suspicious stuff like the inelastic carbon-carbon scattering and the fragmentation functions being notoriously tricky in experiments, and also no prediction available. So yeah, it's a good thing to suspect.
Other questions? Looking to my left.
So, if you have a problem and you need 10 to the 7 qubits or something to solve it, at what point do you start working back on coming up with a better effective theory for the problem? I mean, do you really think that that avenue is exhausted for a lot of the problems you're interested in, say, or and it's really a capacity problem?
This is a good question. I should say that with regards to the QCD calculations, I think that this estimate for hydrodynamics, I think, is grossly pessimistic. I think the real number is more like 10 to the 5. If you think of what you're doing as, I can't find it now. if you think of what you're doing as, I am trying to learn the coefficients that will appear in my true effective theory. See, for QCD hydrodynamics, thanks in large part to Paul Ramachka's efforts, we think we know a very good effective theory for the way in which this relativistic fluid behaves, even pretty far from equilibrium. And it's just a matter of we don't know what the shear viscosity is. We don't know what the equation of state is, although to some precision we do. We don't know what the bulk viscosity is. And we would like to compute those constants from QCD. Now, I don't know of any likelihood of a good intermediate effective theory. So at some point, you have to just say, OK, well, I'll fit the constants on the largest lattice that I can compute. And then I have to go with that. Part of this is being set by you need a lattice in 3 dimensions, which is fine enough to support like the correct high energy behavior of QCD, but also large enough so that you can see a fluid and actually see the viscosity. I've never heard of any prospect for a good intermediate effective theory there. In other cases, yeah, I could see this being the more viable path forward. I think QCD is just a particularly difficult thing to simulate. And you can also look to lattice QCD, which has 30 years, 40 years of history trying to optimize their calculations and look, well, what have they done? Because lattice QCD on classical computers is actually very similar to what we're going to do on quantum computers. A lot of the tricks are just stolen. And there you say, look, they actually have needed historically these very large lattice sizes in order to get trustworthy results for most quantities. Nobody has gotten a 0.3% proton mass prediction on a 4-cubed lattice. So I think some of it is insurmountable. I think that was a very wishy-washy answer, right? Did I do a good job?
Any other questions? It's always behind.
We only have one set of people who are allowed to ask questions.
For the error bars and the predictions, are those error bars relative to experimentally measured values, or are those like expected errors of the calculation where you're estimating some error during the calculation process?
These are expected errors of the calculation, but none of these are cases where the difference from the experimentally measured value is incommensurate with the size of your theoretical error bars. Right, so these are none of these quantities have 5 sigma discrepancies, so these are the same number. I was thinking about the error bars on the calculation when I wrote these numbers down and was looking through papers, but again, these are very ballparked, so it's either number.
Any more questions? We'll look this way. All right, if not, I think we'll stop here. So thanks, Scott, again.
Thank you all.